Now, at the heart of the test that we are proposing is a consideration of a string of coin tosses and asking questions about the likelihood of a run of successes, a subsequence of successes somewhere in that sequence. To begin to make progress, we are going to have to understand how to describe success runs in a neat and compact mathematical formalism. So let's begin by taking a look at a made-up sequence of coin tosses. 1 represents a head or a success, 0 represents a tail or a failure, and what I've shown you on the screen is a sequence of 30 trials. Of course, we are assuming that every trial is an independent trial, and so we're dealing with repeated independent trials, and underlying all of this is a product space and a product measure. Now, in that long string, of course, 1s and 0s are alternating around, they're bouncing around, but in the middle and at the end, we see strings of repeated 1s, repeated successes. And so, clearly, here's an example of a sequence of 30 tosses where there are sequences of 5 or more successes at 1 or more places. To keep an accurate accounting of when success runs occur, we will need to do 2 things. First, figure out what length of success run is of immediate importance. In this case, let us say we're going to look at success runs of length 5, 5 and more. The second, and this is important, is as a convention, we imagine that we start the sequence of tosses on the left, work our way towards the right, looking for 5 successes in a row. The first time it happens, we say, here is a first success run. Here visibly, now marked in red, is an example of what I mean. The first success run of length 5 occurs at trial 9. Now, and this is critical. We reset the clock, if you like, at trial 9. We say we have a renewal, and it's as if we begin the coin tossing anew with trial 10. And then we proceed all the way up to trial 16, where we discover another string of 5 and say, okay, hold it. We have a new renewal. Of course, on trial 16 was the second success run. Now notice there was a success immediately after trial 16, but that is part of the renewal of the next stage of the new sequence of tosses that has started after the success run. We now begin anew at trial 17, proceed all the way till trial 27, where we have the next success run, and we proceed in this fashion. So, at the heart of this idea is that we start from the left with the first toss, proceed to the first occurrence of the success run of length 5 that we are interested in, consider a renewal to have taken place, a new sequence of coin tosses to have been initiated from that point on, what for the next success run, a new renewal, the next success run, and so on. Of course, when we've tagged a success run of length 5, it is possible that it is part of a larger success run. But for our purposes right now, runs of length 6 or 7 are not germane. We are worrying about runs of length 5. And of course, eventually, we'll want to take a step back and tackle runs of any length. But for the time being, let us focus on runs of length 5. Here's one more example of a sequence of 30 tosses. And in red, I have outlined where the success runs have terminated, have occurred. Starting from the left again, on the 10th trial, we have the first success run of length 5. The clock starts again immediately with trial 11. But here we actually have a very long string of consecutive successes. So from 11 to 15 gives you an immediate new success run. The clock starts again. We have a renewal. From trial 16, a new run starts. And you find that we have consecutive successes, culminating in trial 20 with yet another success run. Trial 21 happens to be a success, but we don't quite complete a success run, so we have to move on now all the way up to trial 29, when the next success run comes into place. So this is at the heart of a convention. We go from left to right, and each time we have a success run, we have a renewal. It's as if the coin tosses start anew. Now we understand, we've come to a right understanding of what a success run is in our setting. Now to make probabilistic progress on this, we have to be able to identify what the probability space in question is. And so let's go back to first principles. So here's a sample run of tosses with various success runs identified. The first success run at trial 9, the next success run at trial 16, the next success run at trial 27, and so on. Our very first question, naturally, what is the sample space for this problem? What is the space of idealized outcomes that represents this chance experiment? Now, there are a couple of ways we could go about this, but the most general and extensible fashion is to think of a Gedanken experiment where a coin is tossed repeatedly, indefinitely often. The outcomes of the tosses, call them x1, x2, x3, x4, x5, and so forth, represent successes and failures, zeros and ones. And this entire sequence of zeros and ones will represent a sample point or an idealized outcome for this experiment. Of course, as we've seen in Tableau 6 Part 2, well, that is a dangerous Venn tableau, and if the listener has had the fortitude to walk through it, she would have seen that this leads to actually a very rich and complex space. It actually leads to the continuum. Now, the subtleties of the continuum are not going to be germane for our purposes, but this is just to understand that even simple settings could lead to very complex problems. But in principle, we now have an understanding of what an outcome in this experiment is. Practical simplicity is going to be at hand for us because we are going to essentially terminate the experiment after n trials and ask questions about what happened in n trials, in which case we'll deal with repeated independent trials over a finite domain. Right? But we're jumping ahead of ourselves. Our next question naturally should be, in this space of sample points, what are the events of interest? So let us say that the basketball player in question has taken n shots, and we're interested in whether in that sequence of n attempts at the basket, there is a string of 5 or more successes, consecutive. And so naturally, the event of interest to us is the event that there is at least one success run of length 5 at or before the nth trial. Let us call this event S sub n. Of course, in our sample space, this corresponds to all sequences of trials where in the first n trials, you discover consecutive subsequences of 5 or more ones. Now, connected to this natural event, S sub n, is the event Q sub n, which is the complement of S sub n, which is the event that in the first n trials, there is no success run of length 5 or more. Now we should pause. This event, Sn, is what is germane for us, and we would like to say something eventually about its probability. But that looks like a very complicated endeavor. There are very, very many ways in which one could put in a consecutive sequence of 5 ones somewhere in a long sequence of n tosses. And tabulating and capturing all of them systematically looks to be a very difficult task. Naturally, we will try to break this task up into simple pieces, partition it so that the individual pieces become transparent and we can glue things together. In other words, we're going to try to use additivity by finding proper partitions of the space. A little thought will tell us that we are worrying about sequences of 5 heads, 5 successes, somewhere in the sequence. A natural event of interest, then, is the question of, well, where is the first run of 5 successes? Does that occur? And so accordingly, let's promptly define a new event. anticipating that this just might be useful in stitching together a bigger picture. For each value n, 1, 2, 3, 4, 5, and so forth, let f sub n represent the event that the first success run of length 5 occurs at trial n. Now, there are other possibilities. If you have the nth trial and a success run occurs at it, it could be the first success run, but it could be a second, third, or a subsequent success run. Let's promptly introduce a little more notation to capture this richer possibility. Let u sub n represent the event that there is some success run, the first or subsequent, which occurs at trial n. All right, now we have three events at hand. Sn, its complement, Fn, and Un. N, of course, is an index, and we are allowed to run freely over the positive integers. We'd like to say something about the probabilities of these things. And, of course, naturally, the question is, what is the underlying probability measure that's going to fuel these probabilities? Now, as I've mentioned, the underlying sample space is very rich. It actually spans the continuum of possibilities. But for our purposes, we can afford to look at finite strings of tosses at a time. And what comes to our rescue immediately is the fact that the probability measure is implicitly specified by the fact that we're dealing with a setting of repeated independent trials. For any given n, we are effectively dealing with a product space and a product measure. The computations of the probabilities are going to become almost transparent in consequence of this key observation. And immediately, with this at the back of our mind, let's introduce a little notation for the probabilities of the events in question, just to keep our notation a little more compact, to prevent it from burgeoning. So let's use lowercase letters for the probabilities of the associated events. Lowercase s of n for the probability of the event, big S of n. Lowercase q of n for the probability of the event, big Q sub n. Little f sub n and little u sub n, respectively, for the probabilities of the events, big F sub n and big U sub n, respectively. So before we go forward into a full-fledged analysis of these probabilities, we should begin by exploring the ground, seeing the layout, understanding what we can say about these probabilities in simple settings. What are the boundary conditions that are known to us? So accordingly, let's start by looking at the first few trials, trials 1 through 5. Our immediate observation is the following. We are interested in success runs of length 5. Therefore, it is manifestly impossible that any success run of length 5 concludes on or before the fourth trial. And therefore, the probability is F1, U1, S1, F2, U2, S2, F3, U3, S3, and F4, U4, S4 are all identically 0. What about the possibility of a success run at trial 5? Well, of course, this is possible. And there's only one way in which this can be accomplished, and that is if one starts with a sequence of 5 successes, 5 ones in a row. And the moment this happens, we'll have triggered a first success run, in fact the only possible success run, at trial 5. And the probability of this, because we are dealing with repeated independent trials, is naturally 1/2 times 1/2 times 1/2 times 1/2 times 1/2, or 2 to the power minus 5. Nice and simple. What about the next trial? What can we say about F6, U6, and S6? Pause the lecture while you take this in and think about what the problem setting gives you in this context. Resume the lecture when you're ready. You're back. Let's take a look at a picture. Let us consider the first 6 trials. If there is a success run occurring on trial 5, then in the first row of the table, you will see we must have 5 ones in a row. The probability of that is 2 to the power minus 5. But what if a success run terminates on the 6th trial? Now, if that happens, it is manifestly the case that trials 2 through 6 must give you 5 consecutive ones. But it also constrains what must happen on trial 1. The first trial cannot be 1 itself, because if that were the case, then a success run would already have concluded at trial 5. By a convention, remember, we are counting from left to right and starting anew with a renewal every time we get a success run. So if there is to be a success run at trial 6, we must start the sequence off with a failure on the first trial. But this now gives us a setting where in the first 6 trials I start with a failure and then have 5 consecutive successes. Successes and failures are equally likely. The coin is fair. They each have probability 1/2. And therefore, this particular run of 6, failure with 5 successes, has probability 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Or F6 and U6 are both 2 to the power minus 6. What can we say about S6? The probability that there is a success run of length 5 at or before the 6th trial. And a little introspection tells us that this can only happen if either there is a first success run at trial 6 or there is a first success run at trial 5, which means that S6 is simply F5 plus F6, because these two events are disjoint. They are mutually exclusive. You could have a success run at trial 5, but then you will not have a success run at trial 6, or vice versa. And putting together the algebraic values, we find that we get 3 times 2 to the power minus 6. What have we appealed to? Our universal, subtle, and marvelous principle of additivity. The whole here was a sum of the 2 parts.